All right, let's take a look at another polymorphic example here, a little bit different code, and we'll just add a little bit more complexity as we continue to move forward with our mechanics and semantics here. And in this case, we've got a new interface. It's now called the notifier interface with one active behavior, notify. Again, just that one behavior. Now, this notify behavior doesn't have a lot going on. There's no input. There's no external output there. But the new interface, new behavior. Now, I've got a concrete type named user. And what we see now is on line 22, the concrete type user now implements the notifier interface using pointer semantics, right? But it's the same thing. It's that convention over configuration. So, new concrete piece of data user implementing behavior called notify, which implements the full method set of behavior defined by the notifier interface. Remember, our interfaces are valueless types. Our structs are concrete data types. Now, just like in the other example, I've defined a polymorphic function. I've called it send notification. We really didn't need it, but I need it to show you these mechanics. And again, send notification, our polymorphic function, looks like it's asking for a notifier value, but that's impossible. It can't ask for a notifier value because notifier values do not exist. That's an interface type. It's valueless. So what is it asking for again? It's saying, I will accept any concrete piece of data, any value, or any pointer that implements the full method set of behavior defined by notifier, which is notify. Remember, that's all these polymorphic functions can ask for. Concrete data that implements the full method set of behavior. And then there on line 45, we see our polymorphism play out. Polymorphism means that a piece of code changes its behavior depending upon the concrete data it is operating on. And line 45 can change its behavior depending upon what concrete data we pass through our function. So we go back through the same exercise. We go ahead on line 31. We construct our value of type user. There it is. And then we try to make a call to our polymorphic function on line 36. And when I try to pass that user value through our polymorphic function, the compiler turns around and says, sorry, Bill, I can't do that because that user value doesn't implement the notifier interface. It's saying that that user data doesn't exhibit the behavior that you need. And we're like, what you talking about, compiler? I did everything you asked me to do. I went ahead and I defined a type. It's concrete. There it is, user. I've implemented a method named notify that matches the notify method defined by the notifier interface. There it is. That data absolutely has that behavior, compiler. Why are you doing this to me? And the reality is that from the compiler's point of view, that user value really doesn't exhibit the behavior. And it's because the compiler is trying to protect your program from a massive integrity issue. In fact, every time I see this message, for me, it's really the Go compiler saying, Bill, I love you so much. We're not going to allow this to happen in your software. This is really a message of love. But I want you to understand where this message is coming from, where the integrity issues are. And it has to do with a set of rules that are defined in the spec, defined around the idea of method sets. And method sets define what method behavior that you're defining gets attached to either values or pointers. So in other words, not all of the methods that you define are necessarily getting attached to the data that you're operating on. So let's go ahead and look at these method set rules. I'm going to lay them out the way the spec does. Then I'm going to show you a better way of looking at it. So let's take a look at how the spec defines these method set rules. So what the spec says is the following. If the value you are working with is a value of some type, a value of type user, like we had on line 31, then only those methods implemented with those value receivers are going to be attached to that value. In fact, only values using those value receivers or value semantics get attached to those values of type T. If the data you're working with is an address, you're sharing something, the address of T, then those pointer semantic methods and those value semantic methods, they get attached to the address data. So when you're working with that address of, say, user, of type user in our case, type T, all of the methods you define get attached to addresses. But only those methods defined with value semantics get attached to values. In other words, the compiler is leaving out pointer semantic methods from those values. And this is exactly what we're running into. I mean, if you look at the code one more time, you could see that we've implemented the notifier interface on line 22 using our pointer semantics. All right, using our pointer semantics. The only method we have at play right now is this one right here, our pointer semantic method. But when we look at the call to send notification on line 36, we're passing a value of type user. We're using our T here. And the compiler says, hey, there is no method because I won't include this method. Now the question is, why is the compiler doing this? Again, the compiler is leaving out these pointer methods to values of type T because it really does love you. It says it's trying to stop you from a massive integrity issue. From my perspective, this box shouldn't be a square. This should be heart. There it is, the best heart I can draw. Okay, this is all love. Now there's two integrity issues here. There's a minor one and there is a major one. So let's talk about that minor integrity issue first. What if I told you that not every value that you work with has an address? Just step back and think about that for 1 second. What if I told you that not every value that you work with has an address? If that's true, then that value that doesn't have an address can't be shared. And if it can't be shared, it can't be using methods that use pointer receivers, right? So let me show you this, because it's interesting. There I am defining a type named duration, which is based on an int on line 10. And then on line 13, we implement the notifier interface using pointer semantics. There it is. But more importantly, on line 18, I take the literal value of 42, convert it to a value of type duration, call the notify method against it, and the compiler says, sorry, Bill, I cannot execute line 18 because I cannot take the address of 42, even though it's been converted to a value of type duration. Why? Remember our topic on constants. The literal value of 42 is a constant of kind int. And even though we've converted it to a constant of type duration, it's still a constant, which means it only exists at compile time. And if it only exists at compile time, it's not on the stack, nor is it on the heap. And if it's not in memory, it's not addressable. So the side effect for how we implement constants created a situation where we can't necessarily take the address of every value that we're working with. And integrity is about having something 100% of the time or not at all. And so the compiler, from a minor perspective, is saying I can't attach these pointer receiver methods to values because I can't assume that 100% of the time I can get the address of that value of type T. Now, what is the real major issue here? Because that's a minor issue for me, but there's actually for me a bigger issue at play. And to see the major issue, what I'm going to do is kind of mark out just this area of our chart. And if we read this chart from right to left, if we focus on the behavior, remember anytime we're talking about decoupling, we should be focusing on the behavior, right? It's the difference between saying I care about the data based on what it is, or I care about the data based on what it does. And when we're talking about decoupling, it's about what it does. So if we just draw this out here and focus on the behavior, something really interesting happens. And what this chart is now telling us is the following. If you chose pointer semantics for the implementation of your concrete data, and remember, we choose the semantic immediately after we define the data. Remember, we cannot write a single line of code without understanding what semantic is at play. So what we're saying here is, if the semantic you chose was pointer semantics, then the only thing you're allowed to do moving forward is share that data. Remember I told you I have an absolute rule that you're not allowed to go from pointer semantics to value semantics, that is a major integrity violation, look at what this chart is saying. It's saying if you chose pointer semantics, the only thing you're allowed to do is share. It's holding true to that guideline, that once you're in pointer semantic mode, you're not allowed to make copies of the values that the pointers point to. What it's also trying to say is, if value semantics were chosen, then make copies, store copies inside that interface. Don't share it. That's the right thing to do. But there are times in those small cases, remember when we talked about decoding and unmarshalling, where even though we're in value semantic mode, it might be necessary to share. It's really interesting what this chart is doing. The love that we're seeing here is all about the compiler saying that if you're in pointer semantic mode, the only thing you're allowed to do is share. You're not allowed to make copies of data when you're in that mode. So we cannot be including those pointer semantic methods for those values, because that would violate this massive integrity issue in our code. And this is what the compiler is trying to prevent us from. So if we go back to the original code that we had here that wasn't working, again, there's our interface type notifier on line 11. There's our concrete type user on line 16 that implements the notifier interface on line 22 using pointer semantics. And now we know that if we implement that interface using pointer semantics, the only thing we can do is share. If we try to make a copy of something, then we're going to have that integrity issue. The compiler's not going to let us do it. And that's exactly what's happening here. What semantic is at play on line 36? Well, our value semantics are at play, right? We're trying to make a copy of t, and the compiler says, sorry, that's not going to work. So if I change us out here to using our pointer semantics on line 36, then guess what? The code works. Because now we're in line with the right level of integrity. We're in line with our data semantics. It's really amazing. It's amazing to me that this language is it's really a decade old from the time that they started. This, in November of 2019, this language turns really 10 years old, okay, from the first announcement of the language. And it's amazing to me how the language designers knew about these data semantics and knew how important they were, to the point where these types of things right here, like our method set rules, are buried deep into this language to keep our data semantics clean and have the compiler there to protect you from making these mistakes. The compiler can't protect all of the mistakes, but one of the biggest things that I want us to take away from everything we've talked about is that at a micro level of code, we want to make sure our data semantics are clean. The compiler is trying to help us, but we still have to do our part to make this happen.